So, in this course we are going to learn analog and mixed signal design. Now, as you understand that this course is aimed at giving you an overview of the behavior of MOS devices more from a functional point of view rather than going into the structural details, and then use the terminal behavior of MOS devices to design and analyze the behavior of various analog electronic circuits. So, we shall start off with our discussion on the overview of MOSFETs, and then we shall move on to the analysis of different electronic subsystems. So, first we shall talk of MOS devices. So, just to have a quick recap of the behavior of MOS devices, if I consider an NMOS transistor, then it consists of a p-type substrate with two densely doped N diffusion regions on it. Then you define the source, gate and drain, and so it's a MOS is, as you know, is a 4-terminal device. So, you have source, gate, drain and bulk. Now, if you want to analyze the behavior of this device, if you connect the source and drain to ground and apply a potential to the gate and keep the bulk in the ground, then you will see if this is a negative potential, then once you apply a negative potential, it will attract the holes in the p-type substrate towards the interfacial layer between the oxide and the substrate, and you will see that an accumulation of holes have been formed. So, this phenomena is called accumulation. Now, as you reduce the negative potential, you will see lesser and lesser concentration of holes, and at a particular voltage known as the flat band voltage, you will see that the entire layer of holes is wiped off. Now, if you apply a positive potential, it will repel the holes away from the interfacial layer between the oxide and the substrate, and a depletion region is formed at the interfacial layer between the oxide and the substrate. Now, as you go on increasing the positive potential, the thickness of the depletion region becomes more and more, and you will find lesser and lesser electrons in the depletion, lesser and lesser holes in the depletion region, and at a particular potential, the density of charge carriers in the depletion region becomes so less that the concentration of electrons supersedes the concentration of holes, and we say that this layer gets inverted at that potential. So, this potential is known as the threshold voltage, and the phenomena is known as inversion, or more popularly strong inversion. Now, if you further increase the positive voltage, you will find that a stream of electrons rush from the source and drain and accumulate at in the interfacial layer between the oxide and the substrate, and you find a sheet of electrons is formed at the interfacial layer between the oxide and the substrate. Now, this sheet of electrons will, however, not flow because there is no electric field being set up across the substrate to enable a drift of electrons. So, now if you want to have this sheet of electrons to move, you have to maintain a potential difference between the drain and the source. So, the terminal in which we apply the more positive potential, we call it the drain. The terminal in which we apply the less positive potential, or more popularly the ground potential, we call it the source. So, actually this source and drain are reversible, although in simulators you will find that they expect a particular terminal to be designated as source and the other terminal as drain, but in principle drain and source are mutually reversible terminals. So now if you apply a positive potential at the drain with respect to the source, then these electrons will be drifted towards the drain and a drift current is being set up through the substrate. Now this drift current is basically the drain current of MOS transistor. Now if you consider the potential across the channel, then the potential across the channel is given by VGS minus VT at the source end and VGS minus VT minus VDS at drain end. At source end, VCH equal to VGS minus VT, at drain end VCH equal to VGS minus VT minus VDS. So we find that the potential drop across the channel is more at the source end and less at the drain end, and therefore the channel is not rectangular parallelepiped in shape but somewhat tapered towards the drain. So if you take a transverse section across the MOS device, you will find that it basically takes the shape of a trapezium, being broader at the source end and gradually narrowing down as you approach towards the drain. And okay, so now if you want to write the equations, IV equations for the MOS transistor, then over here the current is called ID because it is the current is flowing, the electrons are flowing towards the drain, which means the current is flowing from the drain. That is why we popularly call it the drain current. It is basically 0 when VGS is less than VT, which basically refers to the cutoff region. This is equal to mu n COX W by L into VGS minus VT into VDS minus VDS square by 2 for VGS greater than equal to VT and VDS less than VGS minus VT. So this is the equation for the active region, and the third one is mu n COX W by 2L into VGS minus VT whole square into 1 plus lambda VDS. This is the equation for the saturation. So over here okay. So now if you consider the behavior of the MOS device, as you increase the drain source voltage, you will find that the drain current keeps on increasing, and on the other hand, since this term is decreasing as you increase the drain source voltage, therefore the channel becomes more and more tapered towards the drain end, and at a particular potential, that is when VDS becomes equal to VGS minus VT, at least mathematically the thickness of the channel at the drain end becomes 0. We say that the pinch off point has been reached. If we further increase the drain source voltage, this pinch off point gradually shifts towards the source, and the point at which the drain source voltage becomes equal to the gate source voltage less the threshold voltage is the pinch off point. But there is a very important funda over here, that is beyond the pinch off point and up to the drain, there is still a conduction because current doesn't stop beyond the saturation point. It still continues almost constant except for a small slope. So that means beyond the depletion, beyond the pinch off point where the depletion region exists, there is a strong electric field which basically drifts the carriers towards the drain, and a very small channel of electrons exist over there, which you can approximate it to be equal to 0. Now, if you see the IV characteristics, then this is basically the cutoff region. This basically refers to the active region, and this basically refers to the saturation region. So this non-zero slope with respect to the voltage axis is basically compliant with this 1 plus lambda VDS term in this equation, where lambda is basically the channel length modulation index, which is also the slope of this transfer IV characteristics over here. So this is all about the basics of MOS devices. Now you could see one very important thing, that is the notion of threshold voltage. So you need to give a minimum of threshold voltage to turn on the MOS transistor. Now if you see the equation of the threshold voltage, you will see that the threshold voltage is again dependent upon something, some parameters. So Vt equals to Vt0 plus gamma root over where phi f is the flat band voltage. So you can see that as you change the bulk source voltage, the threshold voltage also keeps on changing. These equations are very important to find out the transconductance parameters, which we shall do henceforth. So with this we come to an end about the basic operation of the MOS devices, specifically the MOS transistors. Next we shall talk about the large signal and small signal modeling of MOS transistors.